This presentation is about important pKa values. But before I do that, let me talk about the importance of pKa values. We can use pKa values if we want to determine which proton in a molecule is going to be lost first if we treat with base. So which one will be deprotonated is another way to say that. We can assess the charge on an amino acid at a given pH. So we can tell if the groups have an extra proton or a proton taken away based on pH. This is going to be important as well. We can tell whether a given base is strong enough to remove a proton in a molecule. This we can do with pKa values. We can also determine if a solvent is inappropriate for an intended reaction based on the pKa values of the solvent and the strength of the base, which we'll also determine we'll predict that by pKa values. So let's go to some important pKa values, but before I go through the numbers below, let's look at the expression which we've already dealt with in previous presentations above. HA plus H2O is in equilibrium with A minus and H3O plus. And so in this equilibrium, HA is the acid. It gives up its proton to water, specifically to water. We measure the strengths of the acid by how easily they give up their proton to water, and we could use the KEQ values to tell us how strong the acid is. The stronger the acid, the more the reaction will be favored to the right. We did a little bit of massaging. We took the KEQ expression, that is the product of the concentrations of the products divided by the product of the concentrations of the reactants. We took that ratio, we multiplied KEQ and that ratio by the concentration of H2O, and we canceled out H2Os from the equilibrium expression, and KEQ times the concentration of water is we defined as Ka. And so the bigger the Ka, that's like the AQ, the more it's favored to the right in the equilibrium shown above. The weaker the acid, the more it's shown to the left. Weaker acid, it's more reluctant, the HA is more reluctant to give up its proton to water. So the Ka told us how strong an acid was, but we massaged Ka also. We took the negative log of that in order to have an expression that's easily relatable for pKa. So it is a little bit convoluted, I'll grant you that, but the pKa is the negative log of the Ka. So as the Ka gets bigger, which happens with stronger acids, pKa gets smaller. And so the first issue we're going to want to know is the lower the pKa, the more acidic. So I'm going to go through the values in a moment that I want you to memorize, but this is important. Lower pKa, more acidic. So let's go over the table. The first acid that we have in the yellow box is a halide acid. This is HCl, pKa of -7. That's super acidic. That means that the Ka is 10 to the 7th, which means that this is really strongly favored to the right in the equilibrium reaction shown above. The HCl gives up almost all of its proton to the H2O, and so we have almost all H3O plus and Cl minus. And so then we have oxygen acids. These are acids where the proton that's going to be lost, that's the H plus that's going to be lost, is on an oxygen. All of those are oxygen acids in the green box. The pKa's go from -2 to 16. The one at -2, this is really a protonated alcohol, ROH. ROH, this is a hydroxy group on a carbon, and the pKa for the hydroxy group on a carbon is -2. Actually, anytime you see an oxygen that's got a formal positive charge and it's got a proton on it, you're going to say the pKa is -2. We're going to guess that similar structures have similar pKa's, and that's a good guess. The next one below that is called a carboxylic acid, RCO2H. The CO2H is a family of compounds that are acidic, which is why we call them acids, carboxylic acids. pKa of this structure is 5. Now the R group on this one and the one above, this can be either a hydrogen or it can be an alkyl group. The alkyls are carbon chains that have just single bonds on the carbons that are attached to the CO2H. And so this is, for example, a CH3 would be okay for the R group in this particular one. The next one below is phenol, PHOH. That pKa is 10. And the one below that is An alcohol, ROH, that pKa is 16. The ROH, the R can be CH3 or it could be a CH3CH2. It could be a lot of different things. We'll see a little bit more about that later, but I want you to recognize if you have an OH on a carbon, that's an sp3 carbon, the pKa is going to be about 16. There are two nitrogen acids. One of them has a plus formal charge on the nitrogen. That pKa is much more acidic than the one without the plus charge, pKa, and the one with a plus charge on the nitrogen, pKa of that is 9. So it's easy for that to lose its proton. That's much more acidic than pKa of 38. Actually, as a reminder, that pKa of 38 means the Ka is going to be 10 to the minus 38. And so this is very strongly favored to the left. There's very little donation of proton of that kind of molecule to water. The next acid is a hydrogen acid, that's H2, pKa of 35. The next ones are carbon acids. We're going to lose the protons from the carbons that are shown. And so the pKa's vary from 20 to 50. We'll see some variances for carbon acid outside this later, but these are the most important ones. Actually, all of these are important. I think there's 11 or 12 on here. I want you to memorize all of these. Know both the structure of the acid and the corresponding pKa on the right-hand side. So a couple more issues about pKa. It's really important that you know these values are going to be using them for the rest of the year. I don't tell you that often these you should memorize, but this you should memorize. These are approximate values, and so we look at these numbers and they give us a ballpark of where they are. They don't tell us exactly where they are. That depends on what exactly the R group is, for example. So these are average values is what you should say, and we're going to analyze how the R group influences the actual pKa's in succeeding VOSs. And so the pKa's of the actual compounds are going to depend on what the R is, and we're going to talk about that a little bit later. And that's what this last one is. We're going to discuss the impact of structure in later VOSs in this chapter and in later chapters in organic chemistry. So here's this same table. I've just reproduced it in a smaller example, and I've got a structure on the right-hand side below. We're going to do some analysis with that. But first, let me make it a couple of points, and for the third time, let me tell you, memorize those structures and those values now. And recall that the R group can either be an H or it can be alkyl groups. These are groups with carbon single bonds, CH3, CH3, CH2. You'll get a better idea for what alkyl means after the next couple of chapters. And sometimes the R groups are phenols. We've talked about what a phenol is. Phenol is like the ring in the left-hand ring in the structure below. That one is a 6-membered ring with alternating single and double bonds. So that's double bond, single bond, double bond, single bond as you go around the ring. This gives this compound a great deal of stability, part of which is resonance that you should think about, but that kind of ring has a great deal of stability, and so phenyl rings are really unique in this regard. And so notice, for example, as far as phenyl rings, notice the pKa of PHOH in the table is 10, whereas ROH is 16. So there's a big difference that's imparted because we have a phenyl rather than an alkyl group there. So let's go to an example. Let's decide which of these protons on the molecule to the right is going to be lost first. The first thing that we have to do is identify the acids that could lose protons. And so I have oxygen acids with the protons of oxygen acids in reds. We have a nitrogen acid, those protons are going to be in blue. We have carbon acids, those are going to be in black, and there's several types of carbon acids actually. We have the phenyl type of ring. I'm going to call that an aromatic ring. That's the ring to the left. That pKa is, well, what is that pKa? We look to the table to the left and we say, oh, that's a hydrogen on an sp2 carbon of a carbon-carbon double bond. That's around 44. That's what we're going to guess. What about the CH3 on the same ring? Well, that is a carbon with that's an sp3 carbon. That looks like the very bottom one on this table. That pKa is around 50. And we're going to adjust these in later chapters, but that's what we're going to guess for now. The hydrogen on the right-hand ring above, the one that's on the ring, that hydrogen is next to a carbonyl. That pK is going to be around 20. The hydrogen below at the bottom of that ring is about 50. The hydrogen on the carbonyl, we have nothing similar to this in the table, or the table does not tell us everything. So you don't have a good way to guess that. But what you should do is to say, oh, that's probably something like the pKa of a hydrogen on an sp2 carbon, which is around 44. Those protons on the carbons, none of them are very acidic. They're not nearly as acidic as the OH protons on the right and the left. And so the OH proton on the right, pKa of that is around 16. pKa of the OH on the left, that's on a phenyl kind of ring, that's going to be around 10. The pKa of the NH2, so that's a neutral NH2, that's the one below, that's going to be about 38. 38 is a very weak acid. It is not going to be the first one to lose a proton. The most acidic one there is the OH on the left, that is the OH on the aromatic ring, pK of 10. If we treat this with a strong enough base, it'll remove that proton first. And that's how we do that kind of analysis. I wanted to point out to you that we looked at what we thought were the stronger acids, and those are typically the acids on oxygen or nitrogen. So we looked at those first to look for the most acidic proton there. Carbon acids are usually not very strong. Nitrogen acids usually aren't very strong, but we looked at the nitrogen acid as well. In any case, the OH group on the one on the left, pKa around 9, pH of around 9, that's the one that's going to be lost first, the OH on the left. The next proton that would be lost, if we treat it with two strong base molecules, we'd lose the OH on the right. And so the proton that's most acidic is going to be lost first. The next most acidic proton would be lost next if we treated this with enough base. That's how we do that kind of analysis. So if base is added, the first proton that's going to be lost is the OH on the left side. If acid is added, then the most basic lone pair, and that one is going to be the lone pair on the nitrogen, is going to protonate first. The most basic proton grabs the proton first, and so that's the one on the right. So that's how we use these pKa values. We're going to see much more of that in the next couple of slides. This will give you a better feel for pKa's.